Hey everybody, today I'm going to be starting a new series on my channel, which is basically just covering AP Calculus free response questions from the past. I've already made a series on my channel about, going over some AP Calculus topics, but I thought it would be a good idea to make a whole series based on just difficult questions that are, not just kind of like what you learn normally in AP Calculus, but an extension of what you learn, like some of the hardest problems that really make you think. So here's the first one, and it is from last year's exam. So this is the 2022 AP Calculus AB free response, and I'm specifically focusing on question 2, part D. Because parts A through C are pretty standard, but part D was actually a very interesting one that I don't know if I actually, because I did this question because I took this exam. I forget, I'm not sure if I got the right one. I think I did end up getting the method down, but I don't know. Maybe I got the right answer, maybe I didn't, but it's okay. So, the question, I kind of modified the question a little bit just to make things make a little more sense. But let me start over here by describing what's going on. So we have a function ln of x plus 3 and x to the fourth plus 2x cubed. And this is kind of what it looks like. It doesn't label the function, so I guess you're supposed to kind of just figure it out on your own. You can kind of think that, the natural log generally has this sort of shape. So I'm going to call this f, and then the polynomial, especially having, a bunch of like weird terms like that, it'll kind of look a little bit weird, so we can just assume that this is g. If you were not sure, you could plug in some points and try to figure it out that way. But yeah, so they didn't label it. I don't know why they don't do that. I guess you're supposed to figure it out, but whatever. So there are the functions that are relevant to this question. And here's part D. This is an excerpt from part C, just because it gives context. So the region enclosed by the graphs of these two functions, so this region here is the base of a solid. Cross sections of the solid are taken perpendicular. Cross sections of the solid taken perpendicular to the x-axis are squares. So imagine this way. I hope you've seen some of the cross-section sort of questions that they have. But if you look, essentially you can imagine that there is, if you take a cross-section of each of these portions, there's like a square pointing toward you, toward the camera. And so if you imagine like a third axis here, it'll just look like a square. So like this whole thing, I hope you see what's going on here. So there are cross sections. There's a 3D figure that's coming out toward you from this board here. So it's coming out, and then if you slice anywhere vertically, you will see a bunch of cross sections because they're taken perpendicular to the x-axis, so it's like this. So if you cut anywhere along the y-axis or any other certain x value, so like if I cut, I don't know, I don't want to ruin the picture, so I'm just gonna, if I cut here, then like through it, then I'll see it's a square. So hopefully that makes sense. I don't know, I probably didn't explain that very well, but I hope you've seen some of those questions before. So that's what's going on there. And so then a vertical line in the xy plane, so literally just a vertical line here, it travels from left to right, so left to right, along the base of the solid, so along here, moving at a constant rate of 7, they put units per second, but I think meters per second is better. So it's traveling this way at 7 meters per second. Okay, so this is where the mouthful comes in. So find the rate of change, the derivative, of the area of the cross-section. Okay, so the area of the cross-section, we're finding the derivative of that area of the cross-section above the vertical line. Okay, so above being above this way, so up is this way over here relative to there. So if I drew, I'm probably not going to draw this well, but if I drew, let me use a different color here, a cross section here, how am I going to draw this? Like that, it's like a square pointing out this way. I'm not good at drawing 3D, but so just imagine that as a square pointing that way. So they want you to find the rate of change of that area of the cross-section as you move along with respect to time, and when the vertical line is at x equals negative 0.5. So let me draw this here. The line is about here at x equals negative 0.5, okay, and it's moving, right? So we just kind of paused time there, and we want to find how the area is changing at that particular moment with respect to time. Hopefully that clears it up. There's a lot going on in the question, so I think that a lot of people that I knew had a lot of trouble with understanding the question, so hopefully I explained it sort of well there. But essentially we are trying to just find that rate of change. So what they're looking for is the rate of change of area with respect to time. So they're looking for, let me just do it down here, dA over dt, derivative of area with respect to time, at x equals negative 0.5. So here's a problem. Time and x. We don't know the relationship between time and x, but we can do a little bit of a trick here to try to convert this into something that we can work with better. So what if we want to have something in terms of x somewhere here? So what if we do this? We say, so let's see, what do we know? Well, we could differentiate area with respect to x, right? Because we can figure out the area here, and I'll go about doing that in a second. So we could do that. So there's derivative of area with respect to time, but then we also have to cancel out dx over dt, right? That way that dx and the dx cancel. Not totally legit, but it works. So we can technically cancel out the dx's here, and then we have dA over dt. And this is good too, because we do know dx over dt. Dx over dt, what do you think it means? So if you think about it, it is the rate of change of position with respect to time. So that's kind of velocity, right? Change of position, so how much you change position with respect to time. So that's velocity. And we know that that's 7, right? So it moves at a constant rate of 7 meters per second. So this is 7. So let me just say this is equal to dA over dx times 7. Okay, so, well, actually, we still need what I'm going to do is I'm going to put this here. We still need to find the derivative at negative 0.5, and then we multiply that by 7. Okay, so what is A? What is the area function? What that's going to be is it's going to be f of x. Here, let me move over here. So it's going to be, well, we'll think about it this way. So the area is a square. It tells us they are square cross sections, right? So we know it's a square. And the square is, well, let's think about it this way. So the square is going to have the same length as its height, right? So if we know the length of the square, we know its height. It's just the same thing. The length is going to be the difference between f and g, right? So that means the height is also going to be the difference between f and g. So the area of a square, so I'm going to do this, I'll do this in blue over here. So the area of a square, I'll call it a of x, is going to be f minus g, so f of x minus g of x, and then we're going to square it, because that's what you do. The length, length times width, and whenever the length and width are the same, that's just length squared, essentially. So that's what we're doing here. It's this length squared. So that's our area. And then obviously we're finding that out at x equals negative 0.5. So this is a question where you can use your calculator. And plus, I don't really want to do a boring computation. So if we figure out, dA over dx at x equals negative 0.5, this is going to be negative 1.325. So if you want to compute that, you would just take ln of x plus 3 minus this in parentheses, x to the 4th plus 2x cubed, take the derivative, square it, take the derivative of it, and you should get negative 1.325. And then if you want to actually find, the actual, what you're looking for, dA over dt, you multiply that by 7, and then the answer you get is negative 9.272. If I can fit it in here, there we go. So negative 9.272. So that is our answer. Okay, and so what does this mean? So essentially, we found that the rate of change of the area of the cross-section above where that line is right now at x equals negative 0.5, while it's moving at that constant rate of 7 meters per second from left to right, that is negative 9.272. So the area of the cross-section is decreasing at a rate of negative 9.272, because that's the rate of change of it. It is decreasing because it's negative. And yeah, so I hope that makes sense. I hope that cleared everything up for you. If you enjoyed this video, then yeah, just let me know and give me some other suggestions. I'd love to do some other types of videos or maybe some other AP questions or anything like that. So yeah, I hope you enjoyed. Thank you so much for watching, and I'll see you in the next video. Bye guys.